Hey everybody, this is a little bonus video to help you with mastery problem number 2 of homework 11. Also, they're currently drilling directly above my office, so forgive the noises. Okay, so again, this is mastery number 2 for homework 11. I just want to make sure you understand how to analyze this problem because it's really important. And I just don't want people running to Chegg just to be like, how do I do this? So I'm going to give you some hints here. Okay, so the problem is there's two discs. And these discs have a diameter of 0.35 meters. And they're separated by a distance of 0.1 meters. Okay, and we're supposed to find... Oh, and they're surrounded by surroundings at 300 Kelvin. And we know that one of the disks, we'll just say the bottom one, it has a temperature of 600 Kelvin and an emissivity of 0.8. And the other disk is insulated. And that's the only information they tell you about it. Okay, so I'm going to tell you two hints. The first one is, this is not an enclosure. What do I do? So, let me show you. We're going to make this into an enclosure because it is an enclosure. So, actually, we're just going to look at this from the side. So, we're looking at this from the side directly, so we're going to draw it in 2D. So, this is our top disk. This is our bottom disk. Okay. We can draw a pseudo-surface. You remember we talked about pseudo-surfaces all around the outside of the disks. So if I were to draw that here, we'll do this in blue. The pseudo-surface would be all around the outside, forming a cylinder. It almost looked like an ice cream cookie. You know what I mean? It would be all around the outside, so you would have a cylinder. And here I've drawn it, so we've taken a cut vertically through this thing. So you see, here's our pseudo-surface, which goes all the way around. Here's our top disk and our bottom disk. So this pseudo-surface will have the temperature of the surroundings of 300 Kelvin. Because the surroundings are emitting like a black body, because this is a small object in large isothermal surroundings. And remember in chapter 12, we talked about how this is like then a black body. This is like a black body cavity, which means that the small object in the middle will have diffuse, perfectly black irradiation falling on it from all angles. So we can pretend like we have a black surface right here emitting inwards with a temperature of 300 Kelvin. And it is black, so the emissivity and the absorptivity are 1. Okay, so that is how you're going to make an enclosure. Notice there are 3 surfaces. Surface 1, our hot surface. Surface 2, our insulated surface. And surface 3, our surroundings, because surface 3 goes all the way around its one complete structure. Okay, so there's one more thing that I want to go over. Which is, well, we see this, and now I'm going to build a circuit. So I'm not going to build this circuit all the way for you, but I'm going to tell you how to solve the circuit. So as a hint, your final circuit is going to look something like this. Okay? Remember, you had 3 surfaces, so here's, what did I call them? Let's write them again. Here was 1, here was 2, here was 3. Remember, 2 is insulated. We talked about this in class, so I'm not going to give that away, but this would be the radiosity of 2. This we will call J1, this we will call J3, this is EB3, this is EB1. Okay, so originally we had, I'm just going to tell you this because this is important. originally your circuit would look like this, right? So you have your 3 nodes for your 3 different surfaces, your temperature nodes, and your 3 radiosity nodes. These are connected, of course, with surface resistances. Those are the 1 minus emissivity over emissivity A. These are connected with geometric resistances, 1 over FA from I to J and I. Now, we can simplify this 2 ways, right? There's 2 things we can do. Number 1, let's look at this circuit. It is an insulated wall. Because it's insulated, then just drawing this portion of the circuit right here, there is some kind of a heat transfer, right, going through here. And that heat transfer is equal to Q net of surface 2. But surface 2 is insulated. There is no way that you can get heat through that surface. Because it's insulated, Q net 2 is 0. Because Q net 2 is 0, this EB2 and J2 are equivalent. Okay, so we can actually remove entirely this portion and write J2 equals EB2. We can even simplify it more. Look at surface 3. Remember, surface 3 has an emissivity of 1. Also in class, so these are the 2 things I talked about at the very end of class, trying to help you with this problem, but I want to make sure you get it, so I'm doing this for you. If we have an emissivity of 1, this surface resistance, which is 1 minus the emissivity over emissivity times area, is going to be 1 minus our emissivity, which is 1 over 1 times area. 1 minus 1 is 0. This resistance is 0. If there is 0 resistance between 2 nodes, then that means they will have the same value. So again, J3 equals EB3. Okay, so this means we can actually rewrite our circuit to look like this. So we still have this original portion, right? Because that accounts for this wall, which has a finite emissivity. And then we're going to actually draw it a little differently, because some of you have said, how do I solve a triangle? Well, with this one gone, all you needed was for that one to be gone. It actually turns into a circuit that you will recognize. Instead of a triangle, I'm just going to break this out. And so we still have these triangle nodes, right? So here's J2, which equals EB2, and here's J3, which equals EB3. Now, instead of drawing a resistor directly there, I'm just going to draw a resistance like this. Here's the resistor between J1 and J3, and then this resistor I'm going to draw like this. Now, do you see how to solve this problem? Right? Instead of having a circuit like we've done before, where we just have had resistors all in series, now we have resistors in parallel, right? So you now need to break this circuit down into an equivalent circuit, which would be EB1 to EB3 with one resistor between them, which would be the total of adding all these circuits together. Now, you cannot add them just together, right? Our total is not going to be equal to, if this is R1, R2, R3, R4, R1, R2, R3, R4. That is not true because they are not in series. These resistors right here are in parallel. So you can add these. You know what? Maybe we should just do it. Because why not? So here's EB1. Here's J1. Here's J2, which is, this is J3, which is EB3. I'm just going to call this EB2. There's a resistor. There's a resistor. Okay, so step 1, we can see how these are in series. So we can add those 2 resistors together to get them in series. and that will give us this. So now we have two resistors in parallel. We can add them, remembering that 1 over R total equals 1 over R1 plus 1 over R2. That's how we add resistors in parallel. So you can add them in parallel, and that gives you this circuit. Now these are in series again, so you can just add them directly, and you get the final circuit we're looking for. Okay, I'm not going to actually do all of this for you. I've already given you probably too much, but at the same time, this is important, and I want to make sure you understand how to evaluate these circuits. So when you have a three-surface enclosure and you break it down into this kind of circuit, that's how you would add it together to arrive at a final circuit between 2 points. And of course, the only reason this was possible was because on our original triangle circuit, we could get rid of one of these, right? We got rid of that one. If we couldn't, then this would be a much more complicated circuit, a triangle, and I don't know how to tell you how to do that, but by eliminating one of these arms, we can turn it into this circuit that has series and parallel resistors, which we can analyze using this approach I've shown here. Okay, well, good luck with the rest of the homework.